Hello everyone, my name is Xin Wu, non-advised public search engineering. Today I will be presenting on the topic, effect of C-side blocking in CMOS process on circuit performance and ESD robustness. Here's the outline of my presentation. I will start with an introduction to ESD, followed by an overview of conventional C-side blocking technology. Then I will discuss our novel C-side blocking design for CMOS inverter ESD potential, present measurement results, and conclude with key findings. Electrostatic discharge (ESD) refers to a transient high voltage or high current event caused by the sudden transfer of electrostatic charge between objects at different electrical potentials. Such events commonly occur when electronic components come into contact with charged human bodies, mechanical equipment, or environment sources. ESD events are characterized by extremely fast rise times on the order of nanoseconds and voltage peak that can reach several kilovolts, posing a serious threat to ICs, particularly in advanced CMOS technologies. The human body model simulates ESD from a charged human. The equivalent circuit includes the capacitor and two resistors, producing a discharge waveform as shown. This model helps evaluate circuit's ESD robustness. The charge device model mimics charge accumulation within a IC itself. Its equivalent circuit and discharge waveform differ from HBM, highlighting the need for ESD potential methods. The ESD design window defines the voltage and current range that an ESD potential circuit must meet to ensure both the reliability and functionality of an IC. The holding voltage of the ESD potential must exceed VDD to prevent latch-out, while the trigger voltage should be lower than the internal circuit's breakdown voltage to protect sensitivity components. The balance is essential to effective ESD potential without compromising performance. Whole chip ESD employs 6 discharge paths to safely divert ESD current to ground or power nodes, safeguarding internal circuitry. These paths are PD, positive to VDD, PS, positive to VSS, NS, negative to VSS, ND, negative to VDD, VDD to VSS, and VSS to VDD. C-side compounds of metal and silicon are widely utilized in the source, drain, and polysilicon gates of CMOS devices to reduce contact resistance, thereby enhancing circuit operation speed and drop capability. As chip size gets smaller, the very low resistance of C-side can cause ESD current to focus in sentence area, especially in the light doped drain (LDD) of most devices. This can lead to higher electric fields, heat buildup, and even damage to the circuit. To solve this, C-side blocking is used to keep high resistance area in the ESD path. This helps spread out the current and protect the circuit from ESD damage. C-side blocking creates high resistance zones, reducing overheating risk in the LDD area and improving ESD robustness. The figure shows a cross-section view of a PMOS fab with C-side blocking as silicon Germany. Source drain showing this approach. However, conventional methods focus on device level potential and lack circuit level development, which our research addresses. To simulate the presence of C-side blocking in the circuit, equivalent C-side blocking resistance will act at the drain terminals of both the PMOS and NMOS devices. The proposed design integrates dual ESD potential mechanism to enhance circuit robustness. First, a dual-diode structure at the V terminal provides low impedance discharge paths to efficient ESD current directions. Second, a 400 micrometer wide ESD power cable circuit is implemented between VDD and VSS. Based on TAT process parameters, the sheet resistance of non-CSIP plus diffusion region is approximately 133 ohms square, and length of N plus diffusion regions is approximately 59 ohms square. A sensing model from the CSIP boundary layer was developed, enabling target resistance of 0, 2.5, and 5 ohm through optimized resistor protection oxide RPO mask patterns. CSIP boundary resistance is equal to RSH times RPO length divided by CMOS width. This approach accommodates various transistor dimensions and evaluates circuit performance under resistor load condition. This table shows design parameters for 500 kHz inverters with CSIP blocking resistors. PMOS width is 300 micrometers, NMOS is 10 micrometers, with a 0.25 micrometers length. As resistance increases from 0 to 5 ohms, RPO length and chip area grow, reflecting trade-off in designs. This slide shows the chip photo and layout for the circuit with 5 ohm CSIP blocking resistance. We conducted H-spice simulation with a 1.8 volts supply, configured for a 50 ohms load and a 500 kHz operation frequency. For the simulation results, we observed that as CSIP blocking resistance increases, the circuit's driver capability decreases. Under a 50 ohm load at 500 kHz, increasing CSIP blocking resistance from 0 to 5 ohms impact the circuit's performance. At 0 ohms, rise time is 56 nanoseconds, fall time is 112 nanoseconds, Vmin is 0.31 volts, and Vmax is 1.14 volts. At 2.5 ohms, rise time increases to 56.2 nanoseconds, and fall time to 112.2 nanoseconds. Vmin remains 0.31 volts, and Vmax dropped to 1.08 volts. At 5 ohms, rise time reached 59.33 nanoseconds and fall time 112.7 nanoseconds. Vmin stays at 0.31 volts, and Vmax further decreases to 1.04 volts. This trend reflects a trade-off between enhanced ESD potential and reduced driver strength and switching speed. We use a TOP system to simulate ESD events between VDD and VSS, generating pulse with 10 nanosecond rise time and 100 nanosecond width. The TOP IV curve shows ID2 value of 3.01 ampere at 0 ohms, 3.12 ampere at 2.5 ohms, and 3.21 ampere at 5 ohms of CSIP blocking resistance, demonstrating improved ESD robustness. Additionally, our resistance increases with higher CSIP blocking resistance, as observed in the measurements. Using the HCE 5000 system, we test HPN robustness, defining failure as the 30% increases in leakage current at 1.8 volts VDD. The results show HPN levels of 4.85 kV at 0 ohms, 5.05 kV at 2.5 ohms, and 5.2 kV at 5 ohms of CSIP blocking resistance, confirming improved ESD robustness with higher resistance. we apply a linear voltage sweep from 0 to 1.8 volts to the input with EED at 1.8 volts. Measurement the current response at VDD. The results show the leakage decreases with increasing Silicide blocking resistance, reaching as low as 4.91 and 4.57 nanoampere at 5 ohms, showing that higher resistance help reduce leakage current. This table compares our proposed circuit with prior works, with Silicide bonding resistor from 0, 2.5, and 5 ohms. Our design achieved leakage current as low as 4.57 nanoampere, standby power down to 8.23 megawatts, and HBM robustness up to 5.2 kilowatts, outperforming reference in several metrics. Our CMOS Silicide bonding design implemented in TSMC 0.18 microprocess, enhance ESD robustness, increasing IT2 from 3.01 to 3.21 ampere, and HBM from 4.85 to 5.2 kilowatts. It also reduced leakage current from 71.87 to 4.57 nanoamperes. However, trade-offs include increasing layer area, reduced driver strength, and higher arm resistance, highlighting the balance between ESD potential and circuit performance.